Okay, and welcome. Mr. Noldy here. Got another calculus technique or problem to show you, and that is when we need to find a particular solution given an initial condition. So these problems are set up so that you always have a differential equation given, and then you have some initial condition. So notice this is an h prime of t, and this is just h of 1. So the way we go about solving this is by taking the antiderivative. So that's something that came before this. So if I took the antiderivative of h prime of t, I'd get h of t. And then if I took the antiderivative term by term of this, let's see, I'd end up with I'd end up with 2t to the fourth. So we increase this exponent by 1 when we're taking the antiderivative and divide the old exponent by the old coefficient by the new exponent. So 8 divided by 4 is 2. Or go backwards, try to take the derivative. If I wanted to take the derivative of this, I would multiply 4 times 2 to get 8, and then t to the fourth would become t cubed. All right, plus 5t. So the constant, when you take the antiderivative, becomes 5t. But the thing we always have when we take an antiderivative is a constant of integration. So that's what this initial condition is for. We're going to use this to figure out what this c is. So h of 1 is negative 4. So I'm going to substitute negative 4 here. So the next thing we'll do is substitute a 1 in place of the t. So let's do that. Plus 5 times 1 plus c. So just simplify this, right? You have 2 times 1 is 2, and 5 times 1 is 5. 2 plus 5 is 7. So subtract that on both sides. You'd have negative 11 is the constant of integration. So now I can go back here. This is called my general solution, right? General solution here. So I need to plug this negative 11 in place of this c so that I can get my particular solution. So it starts off with 2t to the fourth plus 5t, but then I have negative 11 to put in here, so that's minus 11. So my particular solution, all right, this is what this is about, finding a particular solution given this initial condition up here. So final answer right here. So let's look at, let's look at one that has some fractional exponents. We'll show you how those work as well. Okay, take 3 here. I'm not sure where those balloons are coming from. So here's an example that has a fractional exponent. It's negative on top of that. But notice my my first differential equation is a second derivative. So that means I'm going to have to take the antiderivative 2 times. So I have an initial condition that deals with the first derivative and an initial condition that deals with the function. So the first thing we do is the same as we did before. I'm going to take the antiderivative on both sides of this equation, and I will end up with, let's see, x to the negative 1/2. This would have to be a negative 2 because negative 1/2 times negative 2 is my positive 1 right here. And then as always, don't forget, plus a constant. So now I have a general solution for the first derivative. So I'm going to go and substitute in for that. This becomes a 1. This becomes the x becomes a 0. So we're going to go ahead and substitute that. So let's see, negative 2 times 0 is just 0. So c is going to be equal to 1. So that means I have a particular solution for my first derivative of negative 2x to the negative 1/2 plus 1. All right, one more step here because I have one more initial condition to use. So let's go ahead and take the antiderivative. So the antiderivative of the derivative is the function. And let's see, term by term here. I would bump this up to a 1/2. And half of negative 4 is negative 2. Or take the old coefficient, divide by the new exponent. You could get it that way. Constant of 1, antiderivative becomes an x, and plus c. So now I'm going to use this initial condition up here. Yay. So negative 4, well, let's put the f of x in there, 6, negative 4 times 0 to the 1/2 plus 0 plus c. So 0 plus 0, so c equals 6. So now I know my final answer. I know that f of x is going to be negative 4x to the 1/2 plus x plus 6. So this is the the particular solution to this original set of differential equations. Well, differential equation and then two initial conditions. So let's look, do you want to look at a trig function? Let's look at a trig function. I like your attitude. All right. Okay, example number 3, some trig functions. So again, my first differential equation is f double prime of x equals sine x. So that means I have two initial conditions I'm going to end up using for this. So take the antiderivative of each side. That will give us f prime of x equals negative cosine x plus c. So the derivative of the negative of cosine is positive sine. So now I have to use this, and I have a 1 to go in place of the f prime of x, and that occurs when the cosine of 0, So what is the cosine of 0? The cosine of 0 is 1, but I have this negative that comes along for the ride, right? And the cosine of 0 is 1. So, can I solve that? Yeah, we can solve that. Add a 1 on each side. C must be equal to 2. So, my first part here, my first particular solution, if we want to call it that, is negative cosine x plus 2. So now we're going to go here and use this initial condition, okay? So that initial condition says that my function is 5 when, oops, I forgot to take my antiderivative. Antiderivative of f prime of x is f of x. And the antiderivative of negative cosine x is negative sine x. That's plus 2x plus c. Oops, I forgot an x here. So now I'm going to use this. This is my initial condition for the function. So I'm going to go ahead and say that this equals 5 whenever the sine of, we're going to have a sine of 0 plus 2 times 0 plus c. So the sine of 0 is 0, and the opposite of 0 is 0, and 2 times 0 is 0. So c just equals 5. So I'm going to go ahead over here and write my particular solution. I'd have negative sine of x. Let me make sure that my negative doesn't run into my plus sign. So negative sine x plus 2x plus c, which is now we know is 5. So this is our, can we see that? Negative sine x plus 2x plus 5 is the final answer. And that's finding a particular solution when you're given some initial conditions. So it always starts the same. It always starts with a differential equation and 1 or 2 or more initial conditions, depending on what we're starting with here. All right, so hopefully you got some value out of that. Go ahead and smash the like button and share this with your classmates, please.